Good morning, ladies and gentlemen. Today we're looking at graphing half-planes, as the textbook calls them, or as most people call them, linear inequalities. Now, a linear inequality typically looks like this. Y is greater than or equal to 2x plus 1. And today we're going to show how to draw that graphically and represent it on a graph, or a Cartesian plane. And a good place to start this is might be considering a very similar equation that we're quite used to seeing. Y is equal to 2x plus 1. Now y is equal to 2x plus 1, we know, goes through y-intercept of 1, and then you go across 2 up 1. Sorry, across 1 up 2 to there. And essentially, this is our line. It's big and red, and I'll delete it in a second. But what that really means is that for any given x value, that returns a y value that makes this equation true. Say, for example, if I put in x equals 3, up here should be, if I've drawn the line properly, y equals 7. Clearly the line's not right, because y is equal to 2 lots of 3 plus 1, y is equal to 7. And I can pick any x value here, and that will correspond with a single y value. And that's what makes this a straight line. It's essentially listing a whole set of solutions to this equation. It is giving all of the infinite solutions to that equation, all the possibilities. So for every possible value of x, there is one and only one possible value for y. Alright, so how does that differ from this? How does that differ from the inequality? Well, let's just clean away some of the mess I've made. Here, instead of having just one possible solution, there are in fact many, and I'll show you why. Take the line, I'll put it in, I'll try and put it in a little better here, goes through 1, and there. Not a huge amount better, you'd do better with a ruler. Here, there's more than just one possible solution, because we're not saying that y is equal to 2x plus 1, we're saying that y is greater than or equal to 2x plus 1. That means if I put an x value of 1 in, one possible solution is a y value of 3. And that would be a solution here also, because if y equals 2 lots of 1, don't know what I'm doing, brackets there, plus 1, that's equal to 3. That would be the solution there, and that holds true here as well, because that satisfies this particular inequality. However, there's more than that, just that satisfies it. So if x is equal to 1, y could be equal to 4, or 5, or 4.5, or 6, or 7, or 8, etc. Anything above that line satisfies the inequality. Similarly, if I pick x is equal to 2, that would be an acceptable solution, the 5. Also, everything above that. And it works out that if we're going to graph an inequality, everything this side of the line becomes an acceptable solution. Say, for example, x is equal to minus 1, then we can put it into this equation here, which I've circled a million times already, and what we would get out is y is equal to minus 1. So that would be one acceptable solution. But because of the inequality, anything above that is also acceptable. So, we show this by simply drawing a line as you would with a linear equation, and then shading the side that we want. Couple of little changes. Note how this says y is greater than or equal to, and we represented that on a number line like this, by doing a greater than or equal to as in a coloured in dot. Here we represent a greater than or equal to on a Cartesian plane by doing a solid line. You note how that red line I've drawn here, that red line is solid. If it was a strictly greater than, I would have drawn a red dashed line, indicating that we can't quite have that line as a solution, but everything above it's fine. So there is therefore no equal to solution, simply a greater than solution. Alright, so to graph one of these lines, you need to, first of all, plot the line like you would for a linear equation, and ensure it's dashed or solid according to the type of inequality. So here, it's a strict inequality, so I'm going to go with the dashed line. I know that it will pass through the y-axis at 3, and that for every 1 I run across, it'll drop 4 down. So I'll pass through here, run 1 across, drop 4 down. And then this becomes a dashed line. Now it's a matter of thinking, well, which side of the line do we shade? Is it always above, always below? We're not sure. So instead we pick a test point. Now a test point is any point on the line, any point on the Cartesian plane rather. Typically people tend to use the origin because it makes life easy. So for now, let's just use the origin. And what we're saying is, given this equation, y is less than minus 4x plus 3. If we substitute in the origin, which remember is the point 0, 0, does this equation hold true? If it holds true, that's the side we want to shade. Alright, so let's sub it in. 0 is less than or equal to minus 4 lots of 0 plus 3. 0 is less than or equal to 3. Yes. Tick. So that means we want this side. Everything on this side is feasible. Let me show you what would happen if we picked a point that wasn't in the feasible region. If we picked a point, say the point 3, 3, up here. What we would do is we would say y is less than minus 4x plus 3. Sub in the points. 3 is less than minus 4 lots of 3 plus 3. 3 is less than minus 12 plus 3. 3 is less than negative 9. Now that's not true. 3 is not less than negative 9. That is not a possible solution. So what we're saying is that out this side with this point, that's not possible. Therefore, we want the other side. And you would shade it in nicely. Alright, so sub in a test point, shade the region required. Your test point shouldn't be on the line, because subbing in a test point on the line doesn't help you at all. Typically, origin is the easiest to choose. Then include a key, because it's not always very clear, and this will become much more important when we do the next video. You need a key to show what region is required. So you would say something very simply, little box, region required. And you would shade that little box in the same color you shaded the region you want. Alright? Now, no one-note question for this video, because we're going to do a couple of videos in quick succession. But that is just an introduction to shading linear inequalities, and that's the process to go through. Plot the line, making sure it's dashed or not dashed. Test point, shade ridge required, key. Thank you very much.